SABIC has announced some changes to the existing lantern. As such, the new model will be trialed. Other brands of similar lanterns is also considered for future trials. Although the battery use kept working, its internal condition raised doubts as to its resistance to vibrations and impacts. A battery that should better withstand impacts and vibration has been developed, manufactured, tested in laboratory, and is already in service. Regarding the marking, testing will be carried out over the coming years to evaluate other types of reflective materials. Our plan is to produce and deploy the short model for larger scale trials. The Canadian Coast Guard has high hopes for this type of buoy that may significantly reduce its floating aids program costs through partial elimination of the requirement to deploy 2 buoy systems. This buoy may actually replace current buoys and alleviate the stress imposed on our fleet operation during fall and spring peak periods. It is conceivable that this new buoy model will eventually be used elsewhere in Canada, in places subjected to strong currents and river-mouth ice impacts. It is also conceivable that these buoys will be used profitably in locations where buoys are often hit by tugs and barges or drifting wood. This is the end of my presentation, and I welcome any question you may have. Thank you.
Thank you, Richard. You provide a somewhat scary view of the difficulties of providing buoys to those of us in warmer climates. Our next speaker is Jonas Lindberg. Jonas has been involved in the development of visual aids to navigation since he joined SABIC in 1997. He's been in charge of the development of flashers, user interfaces, as well as remote monitoring add-ons to visual lights. He is responsible for the technology within the ATON department in SABIC, and he is also involved in technical support and sales for key customers. This afternoon, he is going to speak to us about ultracapacitors as energy storage in self-contained lights. Jonas, take it away.
Thank you, sir. Ladies and gentlemen, I will start with a question. Is there, can you see a hand? Is there anybody that hasn't heard this presentation in our stand yet? I mean, I have had it, a number of times. Okay, we still have some, so then I move forward. So, why do we search for a replacement for today's batteries? Well, there is a number of issues in regards to conventional batteries in HD navigation use. Limited lifetime, especially in high temperatures. The battery is often the component that will limit the lifetime of the lantern. Limited number of charge cycles, reduced performance in extreme temperature leads to an oversized battery if the battery, or if the lantern rather, is used in a wide temperature range. And it is very difficult to measure the degradation without using add-on equipment, which means that you will not easily know the degradation and the expected lifetime of the battery. And there are issues with environmental, such as heavy metals. In the following slides, I will give a brief introduction to ultracaps. I will say a few words about the key components that could be used to build a working solution. Our research and tests were conducted using a small lantern, and I will present that as an example for you. And finally, round it up with some conclusions. So, an ultracap or supercap is a little bit different than a normal capacitor. Compared to other capacitor, it has an extremely large surface area and therefore much greater capacitance. The energy density is still not as high as in conventional batteries. In a size of a glass, water glass, we only have about 4 ampere-hours of energy. The UltraCap does not behave like a normal battery that only has a limited drop in voltage until it is fully discharged. It has the same exponential discharge curve as a normal capacitor. This means that the internal power supply of the lantern should be designed to have a very low minimum input voltage. The energy stored mechanism of an UltraCap is not a chemical reaction. It only moves charge and ions. It can therefore have up to 1 million recharge cycles. And the charging efficiency is also very high, approximately 99%. They can be charged fully in less than 1 minute. It is also mechanically robust. It has a very long lifetime, a wide temperature range with almost full performance over the whole range. But one of the main concerns and a major reason to why the UltraCaps has not yet been deployed widely is the big leakage current. With the initial self-discharge rates of 0.1% per hour, it will actually discharge itself in approximately 1.5 months. But, and here is a key point, this figure is only true for fully charged UltraCaps. Tests have shown that the leakage current has a very interesting behavior. The leakage current will drop dramatically as soon as the cell voltage drops below the maximum voltage. The energy loss after 1 year was measured actually to only 33%, and these tests were conducted using a 2.5 volt 3000 farad Maxwell UltraCap. So, with the limited energy available, it is of course extremely important that all parts in the lantern are well energy optimized. The 2 blocks here at the left, they are the ones that need special consideration when designing an UltraCap lantern. The tricky part is the step-up converter. It has to be designed to have a very low minimum input voltage, and in the same time it must behave like a DC load from the capacitor point of view. This can be done by adding a suitable filter in front of the step-up converter. Without this filter, the performance of the UltraCap will decrease. On the other hand, the solar charger can instead be much simpler compared to a conventional one. The only task here is to measure the voltage across the UltraCaps very precisely and just disconnect the solar panels when the maximum voltage level is reached. When the capacitors are connected in serial, there is a need for a separate balancing board that will ensure that no single cell will be overcharged. For the research and test, we use the housing from our small 3 nautical mile lantern and build a 2 nautical mile UltraCap lantern for test and research. The performance of the test setup was 300 milliwatt power consumption during a flash and only 5 milliwatt of power consumption between flashes. And the input voltage can drop as low as 0.5 volts. And now a bit of figures. So we had in this small lantern room for 3 pieces of capacitors, each the size approximately this glass.